Okay, in this video we will again have a look at differential amplifier with differential input. So this is a differential amplifier. Okay, why we are considering it as a differential input is, if you can see, there are two inputs, V in 1 and V in 2. Those two are actually given with a different amplitude is same, but these two are still different because this is VID by 2 and this is minus VID by 2. So that's why we call this configuration as differential amplifier with differential input. And then we are assuming a tail current of 1 milliampere. Since M1 M2 both are matched, and if the values of RD are also identical, so then this current 1 milliampere will be equally divided between this M1 and M2 as 500 microamperes each. So that's what I'm writing here. ID1 is equal to ID2 is equal to I by 2, which is 500 microampere. Of course, we have assumed the value of W by L of these two transistors as 100 micrometer and 10 micrometer, which results in a W by L of 10. So assuming the threshold voltage of this MOSFET as 0.4 and the Kp value as 200 microampere per volt square, so having the expression for the drain current in saturation region as half Kp W by L into Vgs minus Vto whole square, so we can actually obtain the required voltage for that will going to develop across gate and source, which will be 1.107 volt. Of course, using this the expression for GM is under root of 2 ID Kp into W by L, which results in 1.41 millisiemens. Since we know the value of GM and we know the expression for the V01, that is single-ended gain at V01 and single-ended gain at V02 is given by minus GM RD by 2, and using this minus GM into RD by 2, so having a value of RD is equal to 1 kilo ohm, so that's what I'm writing here. Assume the value of RD is equal to 1 kilo ohm and this GM as 1.41 millisiemens. GM into RD by 2, the magnitude of the gain comes out to be 0.705. So this is negative. This is the indication that okay, the output voltage is out of phase with the input voltage, that is Vi1 there. Let us actually go to LT-SPICE and try to identify this circuit. This is what we have. So this is if you can see here, so here I'm writing V out, okay, V01 peak to peak, that is the voltage measured at this point. Let me just see these two simultaneously here. Okay, let me just show both of them simultaneously. Now let me just, now this is the input voltage, what I'm just, okay, just a minute. Okay, this is, okay, this is the this is a circuit diagram and the corresponding output voltages. This is V in 1, that is the voltage at this point. This is like actually VID. This is V in 1 is this. Okay, let me just put it. Let me, for the time being, let me delete this. I'm deleting this. Okay, now you can see this is V of V in 1, that is like, okay, this is VID by 2. If you can see, the VID by 2 peak amplitude is 100 millivolt. The peak to peak happens to be 200 millivolt, which is being written out here. You can see here, this is VID by 2, peak to peak voltage is 200 millivolt. If you are actually looking for what is VID, so this happens to be 400 millivolt. So VID peak to peak is 400 millivolt. And then if you see what is the output voltage at this point, if you again measure the peak to peak voltage of this one, so the peak to peak voltage of V01 happens to be, you can just measure it here. Let me just go from peak to peak. This comes out to be almost 280 millivolts. So this is 280 millivolt what I have here. You can see this is VO1 peak to peak is 280 millivolt. Suppose if you take the ratio of V out 1 peak to peak divided by VID, which is 280 millivolt by 400 millivolt, the ratio comes out to be 0.7 will be the ratio. As per the expression also, V01 by VID is minus Gm into RD by 2, which is also minus 0.705. If you can see here, this is the actually the magnitude of these two things. So this is actually 280 and then 400 millivolts, which comes out to be 0.7. So how about this negative sign? This negative sign can be verified by just having a look at the phase of the output voltage with respect to input voltage. Since they are out of phase, so that what is this negative indicates. And if you actually measure with respect to V02 with respect to VID1, suppose if I write again V02 divided by VID, this happens to be Gm into RD by 2. So again, as we know that it is Gm into RD by 2, so here Gm into RD by 2 was 0.705 volt per volt. The magnitude remains the same. Even if you measure V01 peak to peak by VID peak to peak, so it should result in again same magnitude, but you can see there is no negative sign. So this is actually equals, there is no negative sign, so non-existent. Of course, the positive sign indicates that output voltage at this point is actually in phase with the VID, so that we can verify here. So what I'll do now here is I'll take out V01, but instead I will add V0, okay, V02 there. You can just see what is V02. Okay, let me just change the color of that. See here, so since both input and output, you can see this is VID by 2, this is V02, they are actually in phase. So since they are in phase, so I am not having that sign of negativeness, so there is no negative sign. So V02 is actually in phase with VID, whereas V01 is out of phase with VID. Suppose if we measure the differential voltage, suppose if I just measure the differential voltage, that is V02 minus V01 by VID. So what I'll do is I'll measure what is V0. I'll go back here. I'll just take out this. Let me measure V02 minus V01. I'm just measuring the differential voltage. If you can see, this is your differential voltage. Let me change the color to something different. Okay, if you actually measure the differential voltage peak to peak, so now I just write it here. So the peak to peak voltage of V02 minus V01, peak to peak is actually 556 millivolt. This is the magnitude of the peak to peak. Let me just go back here. See now, this is V02 minus V01 by VID, which is actually resulting in the differential gain of the amplifier. So you can write this V02 by VID minus V01 by VID. In terms of gain, this is Gm into RD by 2. This is minus of minus Gm into RD by 2. This results in Gm into RD, which is nothing but, so we will end up with 1.41 is the gain of the amplifier. So this is the gain that what we are looking at. You can see the sign is positive. If you actually find out what is, this is actually peak to peak voltage of the differential voltage. If you actually find out what is VID peak to peak, which we already measured in the previous case because we didn't change the input voltage, this happens to be 400 millivolt. You can see 556 divided by 400, so which is almost coming out to be 1 point. Let me just find out. It is 556 divided by 400, so you can see it's almost 1 point. It's almost 1.39 volt per volt is the gain of the amplifier. So we are expecting theoretical gain of 1.41, so we are getting almost very close to that. This is upon doing the measurements here. This is upon doing the measurements. Okay, suppose if I clearly place them, so let me just put it so that I can, maybe I can zoom this further. I'll just keep it exactly at the bottom, and this is at the peak. It's almost 559. So 559. Okay, if it is 560, then it will be exactly 1.4. Okay, now it is 559 divided by 400. 559 divided by 400 exactly happens to be 1.3975, which is almost close to 1.4 volt. So this way we can able to find out what is the gain of the amplifier, both when you are applying the input voltage differentially. When you are measuring the output voltage at V01, it is a single-ended voltage. The gain is Gm into Rd by 2, and of course it is negative sign. You can say this is V01 by VID is minus Gm into Rd by 2, whereas V02 divided by VID is plus Gm into Rd by 2, and the differential output voltage is actually, suppose if I write the expression for this one, then this is Gm into Rd only, Gm into Rd only. So that's what we have it here. This is a case where we are writing, or where we are applying a voltage which is differential in nature, and you can see the input is balanced in magnitude. So this is a differential input voltage applied, but it is, the magnitude is balanced on both sides. So we can say this type of applying the input voltage as balanced differential input. So the inputs are of same magnitude. It is a balanced differential input signal. So the input signal is differential. Along with differential, it's a balanced differential input because both the input magnitudes are same. Only thing is that they are out of phase. Since they are out of phase, it is differential. Since they are same magnitude, it is balanced one. We will just think of one more type of differential input where Vi1 is different from Vi2. So maybe we can just have a look at this particular configuration of this is now V in 1, this is V in 2, the same analysis, this is minus VSS, this is VDD, and I have a current I. So this is M1, M2, this is RD, this is again RD here. So this is V01, this is V02, and now we can see I will apply a voltage. I'll apply voltage something like this. Now you can see it is plus minus VID. So you're actually applying a voltage between these two terminals. It was not like in the previous case where you have applied voltage VID. Here it is minus VID by 2. Now it's a slightly different case. You're applying a voltage something like this. It is V in, okay, between V in 1 and V in 2, you are applying the whole voltage which is VID. Because you are applying a whole voltage between VID, so you can also this is called as, of course you can also think of this as applying something. You are only applying here, but you are grounding it here. So that will become an unbalanced way of applying the input voltage. So this can also be thought of like applying, you ground this, you apply the voltage of this VID only at this point. You can see it. So now you are applying the input voltage only to this, but this is grounded. So V in 1 is VID, whereas V in 2 is 0 volt. So this is still a differential input voltage that you are applying. Since the inputs are different, that's why it is called as differential input. Since the inputs are not same, I will call it as unbalanced differential input. So this is called as unbalanced differential input. So since the input is different, we call it as differential. Since the input is not same in magnitude, I will call it as unbalanced. So since the inputs are different, it is differential. Since the inputs are different in terms of magnitude, we have a unbalanced differential input. Let us try to understand, okay, what is the gain of such an amplifier which is still having a differential input but it is in balanced nature. Let me just see how does the analysis goes. Okay, let me write the AC analysis of this one. For AC analysis, what I'll do is I will ground the DC supply. I will have this. This is VID. I will apply this between. So now, because you have that DC current source, now it looks like open now. Maybe you can just think of having some RSS. Maybe here also you can just think of this is having some RSS. Even if the value of RSS, whatever the value of RSS is there, it is fine. Since it's a DC current, you are open circuiting and all DC voltages you grounded for AC analysis. Now this is again, now you are applying the voltage, something like this. Now this is now RD here, this is RD. Let us assume lambda equal to 0. So we know that whenever you have this is okay grounded, and if you are seeing up towards the source side, if this is also okay, if you are grounding this also, if you see from this side, we know that if you are looking towards the source with these two are AC grounded, we know that the resistance offered by this is GM. Meaning if you are considering the AC resistance of this is equal to 1 over GM. The resistance offered by this towards this is also 1 over GM. So this whatever VID you have that is being applied to this will see a resistance of 1 over GM plus 1 over GM is 2 by GM is the resistance that is seen by VID. So the amount of resistance thus VID is seeing is actually 2 by GM. So the current that is flowing in these two transistors is nothing but VID divided by the resistance, which is nothing but 2 GM. Suppose if you want to write it as, now this will become of course, sorry, it is not 2 GM, it is 2 by GM. Then this will be GM VID by 2. So this is the value of ID. So we know that since it is open circuit, whatever current that is flowing here, that is ID, which is equal to GM into VID by 2. The same current will flow in this direction. You can see the same amount of current is flowing in this direction. So because the current cannot go in this direction, because this is plus, it is entering here, this is minus, it has to go in the opposite direction. So we have a current ID flowing through both the transistor as equal to GM into VID by 2. Suppose if this is the magnitude of the current which is flowing through both the transistors, now we can see this is the direction of current is going down here, but the same current is going in the opposite direction for this. Suppose if I write it as V02 and this as V01. Suppose if you want to find what is V01 is the voltage drop across this resistor. So can I write this V01 as RD multiplied by the current that is flowing in the opposite direction, which is nothing but minus of ID. So I can write this V01 as RD into what is minus of ID. So minus of ID, okay, just simply substitute what is ID. So let me just write minus here. It is GM into VID by 2. So I have the expression for V01 by VID, which is equal to minus GM into RD by 2. I think you can able to recollect when you actually applied a balanced input voltage of VID by 2 and minus VID by 2, V01 by VID. So if you can see here, this is V0 by VID, which is equal to minus GM into RD by 2. This is when you are applying a balanced differential input voltage. The same expression holds good even if you are applying a unbalanced input voltage. You can see now you are applying a voltage which is not VID by 2 minus VID by 2, you are applying VIT, that is an unbalanced differential input voltage. Whether the input voltage is balanced or unbalanced, V01 by VAD, that is single ended gain measured at this point, is still minus GM into RD by 2. Of course, same thing is true for V02 here. Suppose if you want to find what is V02, it is the drop across this resistor. So what is the drop? It is ID into RD. But what is ID? I can write it as GM into VID by 2 into RD is GM into, sorry, ID into RD, which comes out to be GM into RD by 2 into VID. Suppose if you are looking for V02 by VID, then this is GM into RD by 2. You can see the voltage measured at V02, that is at this point, is actually in phase with VID. That's why there is no negative sign here. So the expression for single ended gain measured at V02 with respect to VID is GM into RD by 2, which is exactly the same in the previous case also. In the previous case also you might have seen that V02 by VID was equal to GM into RD by 2. Here also it is the same. What is the conclusion here is, of course, we can repeat the same thing for V02 minus V01 by VID, which is a differential voltage gain, which happens to be GM into RD. So whether the input voltage applied is unbalanced or balanced differential input voltage, we will going to have the same gains of single-ended gain. Of course, you are going to have two single-ended gains. There are minus GM into RD by 2 and GM into RD by 2, and this is your differential gain. So the expression for the single-ended and the differential gain remains the same, whether you apply a balanced input or an unbalanced differential input. So this is the summary of this particular analysis. So this way we can able to apply either a balanced input or unbalanced input. Make sure that the summation of the amplitude should be equal to VID. Suppose if you assume that you are applying 2/3 of VID by 2, here if you are applying minus 1/3 of VID by 2, then it is fine. So make sure that the summation should be the same, because here it is 2/3, here it is, if it is 1/3, then the entire sum happens to be VID by 2, then it is, then also you'll get the same expression of this. Of course, the differential gain remains the same, whereas single-ended gains will going to slightly change because the magnitudes will be here you're going to have different magnitude, but the overall gain of the amplifier remains the same. So we'll just have a look at these simulations in the next video.